Velan is a global manufacturer of industrial valves with over 1,200 employees and 12 manufacturing plants located in 9 countries around the world. The Velan Universal Steam Trap was introduced for the first time in Canada and the United States in January of 1950. In those days, the predominant steam trap technologies in use were cumbersome, inefficient, and required frequent maintenance. Founder and CEO Mr. A.K. Velan set out to design a steam trap that was suitable for the high pressure and high temperature operating conditions that naval vessels and thermal power plants were being designed around at the time. The operation of this new steam trap was based upon the principle of a free-floating and rotating ball valve placed on the downstream side of a stellite valve seat and being actuated by a multi-segment bimetallic element. The result was a steam trap that combines effective condensate drainage with high energy efficiency and long service life. Energy efficiency and reliability. These are the only two metrics that truly differentiate steam trap manufacturers. Our goal is to help you generate less steam and perform fewer changeouts. That's the Velan promise, quality that lasts. To understand what sets Velan apart, it's essential to look at the other steam trap designs currently dominating the marketplace. The predominant steam trap technologies today are similar to those in use when Mr. Velan set out to change the world of steam traps in 1950. For example, the thermodynamic disc trap is the most popular design used across all industries today. First patented in 1878, the thermodynamic disc trap operates on the difference in flow velocity between a liquid and a gas. When liquid is passed through the trap, the disc is pushed out of the way of the flow, allowing free discharge of condensate. However, when steam or air enters the trap, the velocity of the flow increases and the disc is pulled onto the seat. When the steam keeping the disc closed condenses, the disc is pushed off of the seat and the cycle repeats itself. The cycling action of the thermodynamic steam trap results in the drainage of condensate in the steam line. However, the violent blast discharge results in large amounts of steam being lost during each cycle, as high-velocity steam flow is necessary to end the discharge cycle and close the trap. Many manufacturers of thermodynamic steam traps claim that flashing condensate is responsible for ending the discharge cycle and closing the trap. However, as this flow test on boiler blowdown demonstrates, the thermodynamic steam trap will not close in the presence of saturated condensate. Only steam flow through the trap will end the discharge cycle and close the trap. I need to stop this video right now to explain why that statement about saturated condensate is so important. For nearly 150 years, thermodynamic steam trap manufacturers have built their reputation on a myth that flashing condensate closes the trap. Their literature repeats it, but the data tells a different story. Whenever we told plant engineers that thermodynamic steam traps were losing live steam during every cycle, their response was always the same: exactly how much? Everything changed in 2008. We purchased a high-pressure steam boiler and officially proved what the industry had missed. Thermodynamic steam traps won't close on saturated water. We then devised a test based on a simple principle. Since a pound of steam equals a pound of water, we theorized that by installing a thermodynamic steam trap on a line with no condensate flow, any liquid collected would represent the exact volume of live steam lost during cycling. Between March and July of 2008, we logged 400 hours of testing. Our daily routine was precise. Stabilize the pressure at 100 psig, reset the cycle counter, clear the lines, and collect the discharge. Every evening we weighed the water and recorded the cycles, building the data set that would finally expose the thermodynamic trap's efficiency gap. We then wrote this white paper, Steam Loss and Thermodynamic Steam Traps. We took our findings directly to the source, oil refineries, chemical plants, and paper mills. These facilities rely on thousands of thermodynamic steam traps, making them the perfect candidates for the significant energy savings our research revealed. After seeing our data, one of the top 5 global chemical firms reached out with a challenge. They wanted to see the static steam loss test performed live, right in front of them. We reconstructed the test rig in Houston, Texas, where 2 of their lead engineers arrived to witness the demonstration. The results were undeniable. The live test confirmed every finding in our white paper. 1 week later, those same engineers returned with 6 additional colleagues to witness the demonstration. Once again, the results perfectly validated the findings of our white paper. After consulting with their thermodynamic steam trap suppliers, they challenged our results, claiming a dry line test didn't reflect real-world plant conditions. They requested one final comparison, a head-to-head test between the thermodynamic design and the Velan multi-segment bimetallic trap on a fully saturated line. A new piping design was suggested by the chemical firm and was erected. The chemical firm wasn't taking any chances. They brought their own steam traps directly from their warehouse to be tested live in front of a gallery of 14 engineers. The results of that final test were undeniable and even more significant than what we had originally reported. I later asked their lead engineer why they insisted on such extensive local testing. His response put everything into perspective. Quote, "We have over 550,000 thermodynamic steam traps across our global facilities. If your data is correct, the impact on our corporate bottom line will be staggering." Laboratory test shows not only that steam loss is necessary for the TD trap to operate, but also allows one to measure the amount of steam lost during each cycle of the trap. The average steam loss required for a thermodynamic trap to function is over 0.03 of a pound of steam per cycle. At current energy costs and a cycle rate of 6 times per minute, the amount of steam required to operate a fully functional thermodynamic trap is in excess of $1,000 per year. The amount of steam loss necessary to operate a population of 1,000 thermodynamic steam traps is in excess of $1 million annually. The Velan multi-segment bimetallic steam trap offers an efficient alternative to conventional steam trap designs. Operating on a thermostatic principle, the Velan steam trap requires no more energy to function than is present in the condensate that collects at the drain point. The Velan steam trap uses a multi-segment cantilevered bimetal stack to actuate the ball valve. At ambient temperatures, the bimetal element is relaxed and the valve is open wide, allowing for rapid discharge of cold condensate and non-condensable gases at startup. As the temperature of the condensate increases to within 3 degrees Fahrenheit of saturated temperature, the bimetal element pulls the valve closed. In the presence of live steam and saturated condensate, the valve remains closed tightly. When the condensate in front of the trap cools to 4 degrees Fahrenheit below saturated temperature, the line pressure overcomes the closing force of the bimetals, and condensate discharge resumes. The Velan multi-segment bimetallic design cycles every 2 to 3 minutes versus every 10 to 20 seconds like other conventional steam trap designs. In the event of a sudden drop of upstream pressure, the valve and seat arrangement act as a check valve, preventing reverse flow in the system. The Velan multi-segment bimetallic steam trap provides rapid, efficient startup of steam distribution drip leg and tracing systems. Due to the advanced design of the bimetallic element, the Velan steam trap collects no more than 12 inches of condensate ahead of the trap at any time, ensuring efficient drainage and preventing the loss of live steam. To better understand this internal operation of the Velan multi-segment bimetallic steam trap, we have constructed a test apparatus to demonstrate the internal workings of the trap. The test rig consists of a steam supply with a constant low-volume condensate flow to the trap of approximately 10 pounds per hour at 100 psig. The piping arrangement includes isolation valves, blowdown valves, and a liquid level gauge for visual detection of condensate. A number of instruments are installed in the pipeline which provide data to a digital video recorder. This digital recorder monitors pressure and temperature variables at various distances from the steam trap. The chart recording demonstrates the efficient operation of the Velan multi-segment bimetallic steam trap. Notice the temperature inside of the trap body at pen 5. This remains below steam temperature throughout the entire opening and closing cycle, preventing the passage of steam across the orifice. However, the temperature of pen 1 at the inlet of the trap rises to saturation temperature at the end of every discharge cycle, ensuring the efficient discharge of condensate from the line. Velan multi-segment bimetallic steam traps offer several advantages over the use of conventional steam trap designs. Chief among these are increased energy efficiency, extended service life, and a high resistance to plugging. When compared to the normal and necessary steam operating losses of conventional steam trap designs, the use of Velan multi-segment bimetallic steam traps presents significant opportunities for cost reduction. Replacing thermodynamic traps with the Velan multi-segment bimetallic design will result in annual cost savings on average of $1,000 per trap. In a plant with a population of 1,000 thermodynamic steam traps, this is a savings of $1 million annually. We've mentioned the potential to save $1 million by replacing 1,000 thermodynamic traps. While that figure is rooted in our rigorous laboratory testing, you don't have to take our word for it. Here is a testimonial letter from a longtime Velan customer that confirms these results in a real-world application. Following the 1990 Clean Air Act amendment, the EPA introduced sweeping regulations targeting oil refining products. By the mid-90s, the industry faced strict new standards for diesel sulfur levels and the rollout of reformulated gasoline, all aimed at drastically reducing smog and toxic emissions. To meet these standards, refineries had to integrate new processing units to remove sulfur. a move that significantly increased their overall steam production requirements. The Murphy Oil Refinery in Wisconsin hit a critical bottleneck. Their boiler house had a maximum capacity of 150,000 pounds per hour, but they were already consuming 142,000. With new units set to come online, they were rapidly running out of breath. In a desperate move to increase capacity, the refinery petitioned the EPA for a new clean air permit to install a larger boiler. The request was flatly denied, leaving them no obvious way forward. As a result, the refinery looked for ideas to minimize steam generation. Following a series of comprehensive surveys and their strategic rollout of Velan multi-segment bimetallic steam traps, the results were staggering. By replacing 1,000 thermodynamic traps, the refinery slashed its steam demand by 20,000 pounds per hour. This didn't just solve their capacity crisis, it added over $1 million directly back to their annual bottom line. The longevity of the Velan multi-segment bimetallic steam trap has been widely known to major steam users for the past 75 years. Since 1950, Velan has been a pioneer in the use of cobalt-based alloys in critical components of valves and steam traps. Stellite 6 is welded into the seat facings of all steam traps manufactured by Velan. The resistance of Stellite 6 to erosion and wire drawing is over 3 times that of induction-hardened stainless steel. The result is a steam trap that routinely lasts up to 3 times longer than conventional designs under the same service conditions. Velan is currently the only manufacturer globally to use stellite as a standard material in the construction of a steam trap, and the value is well proven. Another design feature contributing to the longevity of the Velan multi-segment bimetallic steam trap is a reduced cycling pattern. The Velan multi-segment bimetallic steam trap cycles every 2 to 3 minutes. At 3 degrees Fahrenheit below saturated temperature, the steam trap is closed tightly. At 4 degrees Fahrenheit below saturated temperature, the ball valve gradually opens until the line pressure fully engages the ball valve and causes the trap to open, similar to a safety relief valve. This opening clears any condensate in front of the trap until the temperature of the condensate gets within 3 degrees Fahrenheit of saturated temperature, and then the trap closes. The result is fewer mechanical cycles of condensate and flash steam, which produces less mechanical wear than rival designs operating with violent blast-on, blast-off discharge patterns. The thermostatic operation of the Velan multi-segment bimetallic steam trap brings a number of advantages to plant personnel. Chief among these is a complete resistance to plugging and freezing. The location of the ball valve on the downstream side of the orifice has 2 major advantages. First of all, when condensate temperatures at the trap drop below saturated steam temperature, the bimetals relax and the valve is forced open by the line pressure. This ensures that the failure mode of the Velan steam trap is always in the open position, preventing freezing, waterlogging, and damage to piping and process equipment. Secondly, the downstream valve design prevents clogging of the orifice due to copper oxides or iron oxides present in the condensate. Most conventional steam trap designs locate the valve on the inlet side of the orifice. This is true for inverted bucket, thermostatic capsule, thermodynamic, and float-style steam traps. When copper oxides are present in the condensate, they build a deposit at the point in the system where the condensate flashes to steam due to pressure drop. In the case of conventional upstream valve designs, this flashing occurs inside of the trap orifice, eventually restricting and blocking condensate flow and resulting in the freezing or plugging of the equipment being drained. The Velan multi-segment bimetallic steam trap with a downstream valve design produces condensate flashing after it has passed through the orifice, leaving any hard mineral deposits on the outside of the ball valve and not inside of the orifice. Our field experience over 7 decades demonstrates that facilities that experience a high incidence of steam trap plugging due to copper oxides can reduce or eliminate this problem by changing to the Velan design. So how long does a Velan multi-segment bimetallic steam trap last? Answering that question requires concrete data, specifically comprehensive steam trap testing results. At Velan, we have compiled over 12 years of semi-annual survey data to provide the precise insights you need. At 150 psi service, Velan's multi-segment bimetallic design demonstrates a 10.5-year service life. In comparison, thermodynamic traps on the same service average just over 4 years, meaning our design lasts more than twice as long as standard alternatives. Our data is backed by the 2011 white paper, Steam Traps and Mean Time to Failure, which analyzed a massive sample size of 4,656 life cycles to determine accurate long-term reliability. Velan steam traps are manufactured in compliance with all major international quality standards, using the most durable materials available today. A dedication to continuous product improvement and on-time delivery make Velan a worldwide leader in the design and manufacture of steam traps. For over 75 years, Velan has been the steam trap of choice when durability, rugged construction, energy efficiency, and critical drainage requirements are needed.